Thank you all for getting up early and coming to my final defense talk. My dissertation was about algorithms and methods for influencing a flock. One of the main motivations behind my research is trying to reduce bird strikes in aviation. Bird strikes in aviation are a $3 billion per year issue internationally. And it's not only the damage to the aircrafts, such as engine fires or broken windshields, it's also the delays caused to the passengers that were flying on these flights. So there's many different solutions to reducing bird strikes, such as mowing the grass at airports and using certain types of grass, putting netting over rivers around airports, using bird balls, even putting pulsing lights on aircraft to scare the birds away as the aircraft lands. There's other techniques that can be installed at airports, such as noisemakers right next to the runways, pyrotechnics, scarecrows, as well as baffles that prevent birds from landing around the airport. There's also more human-intensive solutions, such as firing guns to scare the birds or kill them, using lasers to scare the birds away, also using animals, such as dogs or falcons, to pretty much tell migratory birds that this is a dangerous area, they should not come here. Somewhat interestingly, there's actually a 13-week test being ran at Edmonton Airport starting July 1st using a robotic bird. The robotic bird's modeled after a pelican falcon, so this bird should be scaring the birds away from the airport. So this approach is a little bit different than what we're going to talk about in this dissertation, but it is promising that a robotic bird is being used in an airport in common everyday operations right now. So with all this in mind, let's consider the example of a flock of birds that is migrating from wherever they are to a nice warm island, and their natural path is taking them over an airport. Obviously, flying over or near an airport can increase the chance of the bird strikes, the birds colliding with the aircraft. So our idea instead is to add influencing agents to the flock. So robot birds, they can influence the flock to travel, say, over a forest instead of over the airport and still reach their nice warm island. And this approach is different than, say, the rowbird that's being put in at Edmonton Airport, because this approach would try and join the flock as one of its own and guide the flock, as opposed to scaring or hurting the flock. It has actually been shown that flocks of birds will fly with robotic birds as one of their own. In this video, you'll see this robotic bird takes off, and you'll actually see a flock of birds flying with this robotic bird in India. You'll actually see additional birds come in and join the flock to flock with the robotic bird. So this actually shows that it is feasible to design a robotic bird that can be used to influence a flock. So the thesis question addressed by my research is how can influencing agents be utilized in various types of flocks in order to influence these flocks towards a particular behavior, such as avoiding wind farms, airports, things like that. This research falls within the areas of artificial intelligence and multi-agent systems. Specifically within multi-agent systems, we focus on two specific areas, teamwork and swarm behavior. Within teamwork, we focus on ad hoc teamwork, and within swarm behavior, we focus on flocking. And I'll discuss both of these shortly on the next slides. So multi-agent teamwork is teamwork between agents. All of the agents have the same goal. One of my side projects, as Peter mentioned at the beginning, has been working on our RoboCup soccer team. So in that case, we're designing an entire team to play robot soccer together. And most multi-agent teamwork research has considered how to design full teams to perform some sort of task together. Ad hoc teamwork is a specific type of multi-agent teamwork, except in this case, we're only designing a single agent or a subset of agents. And these agents join a pre-existing team and try and accomplish the same goal as the team they're joining. So they have shared goals with this team. They don't necessarily have an opportunity to pre-coordinate with this team. And they also have limited or no communication with the team they're joining. So the scientific question considered by ad hoc teamwork is how to design an agent to productively join a pre-existing team while requiring no pre-coordination with this team. So flocking is the other area of multi-agent systems that this research falls under. Flocking is an emergent swarm behavior, usually seen in terms of flocks of birds, schools of fish, swarms of insects. In all of these cases, the individual agents have simple local behaviors and interactions But when you put all these simple behaviors together, the group behavior appears well organized and stable. And one example of flocking is European starlings. And let's look at a video so that you can see what it looks like. So European starlings tend to have these very large flocks that can change orientation, shape, size, pretty much on the fly. So if a predator comes into this flock, the flock will react almost immediately, even if only a few agents in the flock were able to detect the predator. So before we dive deeper into the research, let's come back to the thesis question. So the thesis question considers how can influencing agents be utilized in various types of flocks in order to influence these flocks towards a particular behavior. You might be wondering how the research in this dissertation relates to existing approaches that other people have considered. So there's been a variety of people that have considered how to simulate flock behavior, pretty much studying the emergent behavior. But our work actually considers how to influence the flock using influencing agents. There's also been other people that have influenced the flock to converge eventually, so the flock can converge very slowly to a behavior. But our work has considered how to influence the flock to converge quickly to this behavior. There's been other work that considers influencing agents that can move quicker than the flock, so essentially a super agent that can teleport from one position in the flock to another. Our work assumes that the influencing agents can move no quicker than the flock, so it's a more realistic situation. And finally, some other research has considered how to influence a flock via heterogeneous herders. So using a similar method as the Peregrine Falcon rover that's being used in Canada. But our work considers how to influence the flock from within by pretty much being one of its own with the flock you're joining. Additionally, outside of these relations to existing approaches, our work is some of the first to determine how to place influencing agents into a flock, as well as how to join and leave flocks. So our work is the first in the novel research in these two areas. So with that in mind, let's move on to an overview of the dissertation. You might be familiar, each of these boxes relates to a different chapter in the dissertation document. You might also remember from the proposal that we did cover a variety of different areas. We considered the problem definition, so defining flocking as an ad hoc teamwork domain. We considered some theoretical work on leading a stationary flock. We considered behaviors for influencing a flock. And we also considered some initial behaviors on placing influencing agents into a flock. I obviously don't have time to cover each chapter of this dissertation in detail in this talk today, so I'm going to focus on two specific areas. These are the areas that are novel to our work. One, how to place influencing agents into the flock, and then also two, how to join and leave a flock without negatively influencing the flock. I will cover what we need to know from the other chapters to be able to fully discuss those two areas. So let's get started with the problem definition. So our problem definition defines the problem of adding influencing agents to a flock as a new scenario for studying ad hoc teamwork. We also introduced different assumptions and parameters that we consider in this work. So first of all agents in a flock have a constant velocity. They have a 2D position in space, and they also have a global orientation at all points. So at each time step, the bird will orient in a particular direction, and then it will move in that direction. It may change its orientation at the next time step, but then it'll move in that new orientation. We consider that there's two different aspects that form a flocking model. The neighborhood model is the first aspect of that. And pretty much each neighbor, or each agent, reacts only to agents within a certain neighborhood around itself. In most of the work in the dissertation, we characterize this neighborhood by a visibility radius. There are different ways you can characterize neighborhoods, and one of the later chapters, a different models chapter, does consider this, and I'll discuss it very shortly at the end of this talk. But a visibility radius, for this pink agent in the middle, the visibility radius would say that the brown agents and the yellow agent would be its neighbors, the ones that are able to influence it. The agents that are outside of the visibility radius, so the clear agents in this diagram, would not be able to influence the pink agent because they're outside of its neighborhood. The second aspect that defines a flocking model is the influence model. So in this work, we say that an agent's orientation at the next time step is said to be the average global orientation of all the agents currently within the neighborhood. This is the alignment aspect of Reynolds flocking model. We'll discuss the different aspects of Reynolds flocking model later in this dissertation talk too. But pretty much the alignment aspect works so that if the brown agent is a flocking agent and the two yellow agents are influencing agents, the brown agent, assuming that these two agents are in its neighborhood, would update its orientation at the next time step to be the average of all three of these agents' current orientation. So as you can see at the next time step, it's facing a lot more southward because it averaged orientations. We do use the Mason simulator. This was designed by researchers at George Mason. The Mason simulator is a very large multi-agent simulation library core. There's a lot of different domains. We pretty much used the Flocker's domain, but altered it to fit our purposes. So now I'm going to move on to leading a stationary flock. I'm not going to go into detail on this, but I do want to have one slide summarizing the work from this chapter. So in this chapter, we set bounds on the extent of influence the influencing agents can have when both the influencing agents and flocking agents are stationary. We contributed an algorithm for orienting a stationary flock to a desired orientation using both stationary and non-stationary influencing agents. And we also introduced behaviors for influencing agents that are outside of any flocking agent's neighborhood. If you're outside of any flocking agent's neighborhood, you obviously currently have no influence. So you want to try and move so that you can influence flocking agents at a future time step. So now I'm going to move on to work on influencing a flock. Again, I'm not going to go into detail on this section, but I do want to introduce the one algorithm that we continue to use throughout the rest of the dissertation. But in this chapter, we contributed algorithms that can be used to influence the flock to orient towards the desired orientation. And we also experimentally considered how to maneuver the flock through turns quickly, but with minimal agents being lost. So this could be thought of as kind of the first step towards getting agents to avoid an airport or a wind farm or agricultural area. I do want to introduce the one-step look-ahead behavior because it will come back a few times in this defense talk. So the one-step look-ahead behavior defines how the influencing agents behave based on their neighbors around them. So the influencing agents consider a set number of discrete orientations that they could adopt. And for each of these discrete orientations, they consider how each neighbor will be influenced. So in order to consider how each neighbor will be influenced, you have to estimate how the other neighbors of that neighbor will potentially influence it. So in the end, the influencing agents choose the orientation that results in the least average difference between the goal orientation and each neighbor's new orientation after one time step. So effectively, this behavior influences the flock towards whatever orientation the influencing agents want it to face very quickly. So this was the work that pretty much could get the flock to influence quickly, whereas previous work could get it to influence slowly. So with that in mind, I'm going to move on to the first section that we really dive into detail in this defense talk, and that's the section on placing influencing agents. In this contribution, we started to realize that the position of influencing agents within a flock affects their influence. Earlier work in the dissertation would randomly place influencing agents into the flock, and we started to realize that we can do a lot better. So this contribution contributed various approaches for placing influencing agents directly into a flock. We also evaluated these methods on different flock sizes, compositions, densities, things like that. So we make a few assumptions in this work. We assume that the flock begins within a set area of the environment. So in this case, you can see the flock is starting up here. We assume the environment's non-toroidal, so the influencing agents, or any of the agents, that might be pointing towards the edges, such as these agents, if they fly off the edge, they're going to continue flying in that direction. They're not going to appear on the other side. We assume that the flock may or may not be cohesive. So by cohesive, I mean flocking together currently. As you can see in the image, some of these agents are facing the sides. So without influence, they're going to just separate and go separate ways. And we also assume that the flock will interact with each other according to the assumed model. For our experiments, this is the alignment aspect of Reynolds flocking model. But as we show in a later chapter of the dissertation, the actual model that we use is not that important. It can generalize to other models. So we consider 5 different types of placement approaches. Again, all of these placement approaches are placing influencing agents into the flock in particular configurations. So we start with some constant time placement methods. You can think of these as baseline methods. In fact, the first baseline method is random placement. So this was what we had used in previous parts of the dissertation. We would randomly place influencing agents within the dimensions of the flock. It's by far the most baseline of the baseline methods. We also consider a grid placement method, which places influencing agents at predefined gridded positions throughout the flock. This method is not flock aware. It's not actually placing the influencing agents based on the current positions of the flocking agents. We also consider a border placement approach, which again is not flock aware, but it places influencing agents around the space covered by the flocking agents. And throughout this talk, I'll be introducing many different results. Unless I specify otherwise, the y-axis is going to consider the average number of flocking agents lost. We're trying to reduce or avoid losing flocking agents, so lower is better on these graphs. On the x-axis, you'll see that there's k and m values. M is the number of flocking agents. Most of our graphs will show that there's 10 flocking agents consistently. And you'll see that in most of the graphs we're varying the number of k agents. K would be the number of influencing agents. We'll usually see lower values of k, less influencing agents, losing more agents. So they'll have higher bars. And we would hope that as k gets bigger and we have more influencing agents, we'll soon lose less flocking agents. And then of course we'll also vary whatever we're showing, which will be shown in a legend. Most of our experiments have 100 trials, and the error bars will be the standard error of the means. But this will always be listed at the bottom for you too. So let's look at the first results. So in this case, we're comparing our different baseline methods. And you'll see that when k equals 2, they all perform about the same. We can't really say that any do significantly better. But when we get to larger values of k, more influencing agents, we start seeing the random approach doing significantly worse. We would expect this because the random approach is placing agents randomly into the flock, to where the grid and border approach are at least separating and spreading out the influencing agents that we're adding. You'll see that for k equals 10, the border approach actually does significantly best. And this is because when you have a lot of influencing agents, putting them on the borders of the flock can tend to corral the flock together, so that if a flocking agent was about to leave, it's likely to kind of be intercepted by an influencing agent as it's leaving, and hence it'll stay inside the flock. The second approach we consider is pretty much the last approach that was considered in the proposal talk. Everything else you see in this talk will be brand new to you. So the graph placement method considers sets of positions in which the influencing agents could be placed, and evaluates how well these sets connect the flocking agents with the influencing agents. So this is the first of our flock-aware methods. The influencing agents are being placed based on where the flocking agents are within the flock. Let's consider it in a little more detail. So step 1 of the graph placement approach is to consider potential influencing agent positions. We consider 2 different types of positions. The first one considers the midpoints between flocking agents, but only if the flocking agents are within 2 neighborhood radii of each other. So let's consider the 2 black agents with the orange agent at the top. Let's assume that these 2 black agents are within 2 neighborhood radii of each other. And that would mean if we place an influencing agent in between these 2 agents, it'll be in both of the flocking agents' neighborhoods. So this would be a good position because by placing one influencing agent, we're able to influence 2 flocking agents. The second potential position we could consider would be near a flocking agent. That could be, as this example shows at the bottom. We place the orange influencing agent right next to the black flocking agent, so we know that it will be influencing that black flocking agent for at least this time step. Once we have these sets of potential influencing agent positions, we have criteria for how we should pick which of these positions in the set should actually be used. So our criteria considers how these agents are connected. When I say connected, I mean that the flocking agent will eventually have the influence of an influencing agent be spread to it. So let's look at this diagram on the right for a little bit. So the orange influencing agent, at the first time step, would be able to influence both of these flocking agents that are marked with 0. And then at the next time step, we know that this agent would spread the influence given to it by the influencing agent to this agent. And then at the next time step, it would be continued to be spread. So all of these agents are considered to be connected. Alternatively, if we had an influence or a flocking agent way down south, if that wasn't within the neighborhood of the influencing agent initially, or within the neighborhood of any of the flocking agents up there, it would be considered disconnected. So it would not be connected. So the first metric tries to minimize the flocking agents not connected to an influencing agent. So we're essentially minimizing the flocking agents that will not have influence spread to them eventually. The second metric would try and maximize the connections between flocking agents and influencing agents. So this would see influencing agents being placed in large clusters of flocking agents, because then you're going to have many connections to flocking agents. So let's consider an example. In this example at the top, I know it's a bit hard to see. I lost my mouse. But the example at the top, you can see that we could place orange influencing agents at all these different positions. And you can see the black flocking agents peeking out from behind some of them. Given all of these positions to choose from, the first metric would pick the positions shown below. And because only one solution would satisfy the first metric, we would not go on to consider the second metric. However, if there had been multiple solutions that satisfied the first metric equally, then we would continue on to the second metric. There's two additional metrics given in the dissertation document, but for ease and time, I'm not going to cover those here. So let's consider how the graph approach performs in comparison to the baseline approaches that we introduced earlier. So you'll see that the graph placement approach, the blue line in these graphs, performs significantly better than the other approaches for all values of k that we consider. And again, this is because the graph placement approach is flock aware. It's placing the influencing agents based on where the flocking agents actually are in the flock. One interesting note to consider is that when k equals 10 and m equals 10, so we have the exact same number of flocking agents and influencing agents, you see that the graph approach loses 0 flocking agents. And that's because we're pairing one influencing agent with each flocking agent. So it's, they have very strong influence over them. Yes?
So when you have no influencing agents at all, how many agents are lost in this case?
All of them in most
all of
cases.
them are lost.
Yes. You may luck out and have the flock accidentally continue south, but you'll at least be averaging nine or so. So let's move on to the hybrid placement methods. This is the first approach that was not considered at all in the proposal talk. So let's move on with this. So the hybrid placement approach uses the graph placement method to choose the first case of G influencing agent positions, and then selects the remaining positions using a constant time approach. So this is effectively trying to use a very flock-aware method, but that uses high computation time to pick the first positions, because these are important. You can place influencing agents in large clusters for these, and then you can use a constant time method to place the remaining agents. In the images over here, the blue agents are placed using the graph placement method, and then the orange agents are placed for the images on the top using the grid placement approach, and for the images on the bottom using the border placement approach. And there's many different ways that you could actually choose which constant time positions you want to use. In these cases, we picked the ones that were furthest away from the graph placed influencing agents. But again, there's many different ways you could choose this. So let's consider how, since this is a hybrid method between grid placement and graph placement, let's consider how the hybrid approaches actually do in comparison to these. Let's start looking at k equals 2. We'll see for this case, placing the two agents using the grid approach does significantly worse than using the other approaches. You'll see the other approaches do exactly the same as each other because they're all placing the two agents using the graph approach. But let's consider, say, k equals 8. In this case, you see that the grid approach does significantly worse, the graph approach does significantly better, and you'll see that the two approaches in between fit as you would expect, because the yellow hybrid approach is placing two agents using the graph approach, whereas the green one's placing 4, so you would expect the one placing using 4 would do better than 2. And we see that the difference is significant here. The next placement approach we're going to consider is the two-step placement method. This method is detailed in the dissertation document, but for time I'm just going to give an overview of it here. The two-step placement approach, as you would expect, uses two different steps. The first step uses constant time methods for defining a set S of possible positions. We specifically consider a large grid set as well as a large border set. There's examples of the grid and border sets over here. And then once we have this full set of positions to pick from, we consider 4 different methods for selecting K influencing agent positions from the set S. So you're pretty much discretizing the area from which you can select positions. I'm not going to share results here. They are in the dissertation document. But we see that our min uninfluenced method of selecting the K positions performs best. In short, the min uninfluenced method tries to minimize the number of uninfluenced flocking agents in the flock. So for, say, the grid placement approach, you would see positions that are next to, say, a few flocking agents being chosen, because then you're going to minimize the number of uninfluenced agents. The final placement approach method that we consider is the clustering placement method. We consider 3 different methods in the dissertation. I'm only going to discuss 2 here. But we use well-recognized clustering methods to identify K clusters of flocking agent positions. In this talk, I'm going to discuss farthest first as well as K means. Farthest first randomly chooses the flocking agent and places the first influencing agent at this flocking agent. So in the examples here, the first chosen agent would be this one, as well as this one. Then on each subsequent placement, we place an influencing agent at the flocking agent's furthest from all previous placed influencing agents. So as you can see in the images on the right, this results in the influencing agents being spread pretty much at the borders of the flock, because they're always placing at the furthest flocking agent from the placements that already exist. K-means, on the other hand, chooses K flocking agents as cluster centers. You can choose these randomly, you can choose them using farthest first. In our experiments, we choose it using farthest first. And then until convergence, we assign all flocking agents to the nearest cluster center, and we calculate the centroid for each cluster. And this centroid becomes a new cluster center, and we iterate over this until we come to convergence. Let's consider some results for this. We'll compare against our previous best method of the graph placement approach. Let's first look at K equals 2 and M equals 10. You'll see for this case, having 2 influencing agents, the graph approach places these 2 influencing agents significantly better than either of the clustering approaches. And that's because the graph placement approach tends to place each agent in the first position that's best, whereas the clustering approaches attempt to separate the flock into 2 clusters. And this may result in actually placing an agent in the middle of these clusters in a suboptimal position. So that's why when you only have a few, the graph approach does better. But if we consider as K equals bigger and we have more influencing agents to place, we see that the graph approach starts doing significantly worse than the clustering methods. And that's because the graph approach continues trying to place agents based on the connectivity, whereas the clustering approaches effectively separate the flock into a variety of clusters, and that tends to perform better. So in summary, yes?
So on those, both K-means and graph are more computationally intensive than the more heuristic methods. How do they compare to each other computationally?
So the graph approach is still going to take a higher runtime than the clustering methods. Obviously that differs with different values of K and M, but the graph approach generally is still going to be more computationally intensive. So that could be another reason. In the dissertation document, there's this big flowchart that pretty much shows, based on runtime, performance, flock size, which method you should choose. I didn't include it for the sake of time, but it's in one of the last pages of this chapter. So in summary, this chapter showed that the position of influencing agents within the flock affects their influence. We contributed various approaches for placing influencing agents directly into the flock, and we evaluated these methods on various flock sizes and compositions. So now we're going to move to the next kind of section that we dive in deep of the dissertation work. And this section is on joining and leaving a flock. So in this section, we consider how influencing agents can join a flock in motion with the goal of altering the flock's orientation. And you might be wondering, why don't the placement methods from the section we just talked about still work here? And the biggest difference is that these placement methods try to put the influencing agents into the middle of the flock. And we found that if we try and use these directly, as the influencing agents are trying to fly into the flock, they become neighbors of the flocking agents. So we see that these influencing agents are influencing the flock as they're joining, and that tends to make the flock splinter. So we could not use the placement methods just straight away if the influencing agents need to actually fly into and join the flock. But we also considered how the influencing agents can leave a flock, which as far as we know, no one else has considered that question. So in this section, we assume that the influencing agents are going to leave a station that's positioned ahead of the flock. This could be a charging station if we think about robot birds. But the station could be down here. It's placed ahead of the flock. We assume that the influencing agents cannot travel faster than the flocking agents, so they can't teleport from one place to the other. And we assume that the flock is cohesive and flocking in a particular direction. So as you can see in the image, all of the flock is traveling southward together towards the airport. In this contribution, we considered two different scenarios. We considered the hover approach. This case would be when the influencing agents are able to hover with a particular orientation at a set position. So that would be just hovering in place. But unfortunately, it's our assumption that some of the robot birds that we might actually be able to use in real life would not have the capability to hover based on their wing design and general design. So we also considered the intersected scenario. In this case, the influencing agents must maintain the same velocity as the blocking agents at all times, so they're not able to stop and hover in place. Just so you can see, I'm going to show you a video of the hover approach. So you'll see that in this case, the pink influencing agents stop ahead of the flock in a current configuration, and then influence the flock to travel towards the goal, which is to the right. For the sake of time, although the hover approach is discussed in detail in the dissertation document, for this talk, I'm going to consider the intersect approach. So in the intersect approach, we assume the influencing agents maintain the same velocity as the blocking agents. So for the intersect approach, we have to consider both the target formation that we want the influencing agents to have when they start to influence the flock. So pretty much what target positions are they trying to fly to before they start influencing the flock. And so of course we need to calculate the desired time to join the flock and begin influencing, because we want all of these flocking agents to be influenced at the exact same time by the influencing agents. So the influencing agents all need to hit this position at the exact same time. We consider 5 different target formations. These are the positions that the orange influencing agents want to have before they start influencing the black flocking agents. I'm not going to discuss these in detail. I'm instead going to just show you videos of each of these working. So again, the pink agents are the influencing agents. The gray agents are the blocking agents. And you'll see the pink agents coming in a line for this approach and influencing the flocking agents to travel towards the goal, which is to the right. So we consider this the push-to-goal line method, and it's essentially pushing the flock towards the goal. I'm trying to ignore the leaving behavior at this point. All of the methods use the same leaving behavior, but I really want you to focus on the joining behavior at this point. We can also consider a forward line method. In this case, the influencing agents are all trying to fit in a line, essentially, that will separate the flock from the airport. So the idea is that the forward line is able to capture the flock to prevent them from continuing south towards the airport. We can also consider a push-to-goal funnel. This is like the push-to-goal line, except it fits in a funnel, with the idea being that we can condense the flock some to make it easier to influence. We can also consider the forward line, but in a funnel. So again, we're trying to condense the flock while also catching it to prevent it from continuing south towards the airport. And then finally, we consider the El Corral approach. This tries to combine the push-to-goal line and the forward line, while pushing the flock towards the goal, while also preventing it from continuing south towards the airport. Yes?
So there are some of these guiding agents that actually depart in towards the airport. They don't maintain that line or that formation. Is that a problem, or why does it happen?
So these were mainly considering the joining approaches, but when leaving the flock, obviously you want to avoid leaving towards the airport unless there's a specific reason to do so. But yeah, leaving we're going to consider at this point.
But was he asking if some of them were going towards the airport? In the videos, it looked like they were all going either directly
usually
away.
go north,
yeah, they're going away or to the side.
Yeah.
You are the flock is splitting.
Yes.
But it's not. But none of the birds are going towards the airport in the end.
Which
Yeah.
is south.
Yeah, they shouldn't have went south towards the airport. No.
I see. Okay, that's true. They don't at the airport. Okay.
Yeah.
It doesn't matter what happens as long as they don't go to the airport. It's not that they have to be in a formation.
For now.
Okay.
Exactly. So in terms of leaving, we consider 3 different scenarios. Of course, if the agents are able to hover, hovering is the easiest. It just lets them hover in place while the flock can continue towards the goal. But in this talk, we're considering that they can't hover, so we consider 2 scenarios. We consider the nearest edge approach, which essentially leaves the flock at the nearest edge. And then we can also consider influence while leaving, which trades off between influencing the flock towards the goal and attempting to leave the flock. Let's consider the nearest edge approach first. So in this approach, we assume the influencing agents know their approximate position in the flock. And when it's time to leave, they orient towards the nearest edge. But as Risto was pointing out, we don't want the influencing agents to leave towards the airport because then they may pull some of the flock towards the airport. So for the nearest 3-edge approach, we consider all of the edges except towards the airport as potential leaving edges. And then the nearest 2-edge approach, we don't leave towards the airport or the flock's desired orientation. Because if you can leave towards the flock's desired orientation, you're clearly going to stay with the flock. And if you leave towards the airport, you're going to potentially cause a bird strike, which you don't want to do either. We can also consider the influence while leaving approach. In this case, we alternate between influencing and leaving. Obviously, if there's no neighbors, you can leave without any harm because you're not influencing anyone as you're leaving. If the neighbors aren't aligned to the goal, or the influencing agent has left the flock for too many previous time steps, we influence the flock for a while towards the goal, so kind of get it back on track. Otherwise, we can leave the flock. Obviously, that may take the flock a little bit off track, but soon enough, we'll alternate back to trying to influence the flock towards the goal. So this method takes longer, but it generally tends to make leaving less chaotic. So there's a lot of different results in the dissertation document. I'm going to present one set of sample results here. Notice that these graphs have different y-axis than the graphs throughout the rest of the dissertation. In this work, we considered 4 different metrics. I'm only going to discuss 2 of them in the talk. But we consider average angular difference from the goal. So obviously, you're trying to influence the flock towards a particular goal. You would like the flock to be facing towards that orientation. So the graph on the right considers how far away the angular difference is from the goal on average. You'll see that in these cases, you tend to see the push to goal line and the push to goal funnel performing best. And that's effectively because these hit the flocking agents on the left and push it towards the goal. So you tend to have a lot of influence that's able to keep the flock angled towards the desired orientation. Of course, you can also predict that we will want to also consider the number of flocking agents that intersect the airport. Obviously, we want to reduce this, minimize it. And you'll see, unfortunately, that using push-to-goal line and push-to-goal funnel, which do best in terms of the average angular difference from the goal, generally don't perform very well on the number of flocking agents that intersect the airport. And that's because the forward line and forward funnel and L corral perform well because they end up placing influencing agents on the bottom of the flock to pretty much separate the flock from the airport. So these approaches are able to catch any agents before they hit the airport. So in summary, this contribution considered how influencing agents should join the flock in motion with the goal of altering its orientation. They also considered how influencing agents can leave a flock while minimizing the damage to the flock as you leave. Now I'm going to very shortly discuss our contributions to the different models work. We present a lot of results in the dissertation document, but due to time, I'm only going to kind of overview it here. So this contribution considered how well do the methods in this dissertation generalize to other flocking models. Specifically, we consider how well do they work with alternate neighborhood models, so different ways of determining which agents around you are considered neighbors, which ones can influence you, as well as scaling up to the full Reynolds flocking algorithm, and I'll discuss both of these in the next slides. But our general question was also, do the influencing agents need to know the true model being used by the flocking agents? By true model, I mean the model that the flocking agents are actually using. Do we need to know that before we join the flock to influence it? In terms of different neighborhood models, our research considered 3 different alternate neighborhood models, and we determined how well our methods work when the flocking agents are using each of these neighborhood models. We found that the one-step look-ahead algorithm, which we discussed earlier in this talk, we found that it generalized to different neighborhood models very well. And we also found that it's not critical that the influencing agents know the true neighborhood model before they join the flock and influence it. We also considered what happens if we use different neighborhood models. So specifically, we considered 3 aspects of Reynolds flocking algorithm. Throughout most of the dissertation, we considered the alignment aspect, where we have the flocking agents pretty much steering towards the average heading of the neighbors. But Reynolds' full algorithm considers 2 additional aspects too. It considers the separation aspect, which has the flocking agents steer away from neighbors to avoid collisions. And we also considered the cohesion aspect, which has the flocking agents steer towards the average position of the neighbors. So when you combine all 3 of these aspects together, you get relatively realistic starling-like behavior. So we considered what happens if the flocking agents are using just one of these aspects, what happens if they're using 2, and what happens if they're using the full Reynolds flocking model. And we found that, in general, it was best for the influencing agents to believe that the flocking agents are behaving according to the alignment influence model, even if they weren't. This is encouraging because we use the alignment influence model throughout most of this dissertation. But I should note that our general metrics of trying to minimize the number of lost agents does fit well with the alignment influence model because that tries to steer the flock towards the average heading of neighbors. So it's not surprising that the alignment influence model is generally the best choice for the influencing agents. That being said, we did find that the methods do generalize well to other similar flocking models. By similar, I mean generally the cluster flocking models. The related work section in the dissertation considers clustering models versus like V-flocking models. This would not generalize well to V-flocking. I can discuss that more during the question phase if you want. But we did find that knowing the true model utilized by the flocking agent is not critical, which is really encouraging. Finally, I'm going to shortly discuss our last contribution, which is a robot implementation. For this contribution, we considered how can influencing agents influence a flock of bipedal robots to avoid a particular area. For this contribution, we used Now robots. They're manufactured by SoftBank Robotics. And we did our experiments on a standard platform league field. It's an 8-meter by 6-meter field. And we essentially had the flocking agents attempt to avoid the center circle. So let's look at a video. So in this video, the orange agent is the influencing agent. You'll see that it's currently trying to turn to the left to influence the flocking agents, the white agents, to also turn to the left. You'll see that the flocking agents are starting to turn towards the desired goal. Obviously, robot experiments can have noise in them, so you'll see some strange behaviors every once in a while as the robots are lost. They may believe that they're going in one direction, but they're currently going in another direction. Everything that they're sensing is real time, so they have to determine where they are on the field based on the lines and goals on the field. But you'll see that the flocking agent has to oversteer to some extent to influence the flock. But you'll see soon that the orange agent, the influencing agent, is going to turn back to influence the flock to kind of go around the circle. They've gotten past the danger zone at this point. But now you'll see him turning, and you'll soon see the flocking agents also turning to the side. Yes?
How did the birds know where the influencing agent is in this case?
So we're considering that there's a radius visibility point. So they're considering everybody, all of the agents that are within 3 meters.
But how do they
We had the
see-
robots communicate between
Okay.
each other, their current orientation, their current position.
Okay.
Obviously, you could use vision to detect this, but we decided just to communicate each robot's current assumption of where they are.
But in this case, if you were using vision, they wouldn't see because they're because it's behind.
Yeah, but you could use, say, a visibility sector
Right.
neighborhood. But we tried to make it as friendly of a domain as possible by using a 3-meter visibility.
How do the real birds know what's behind this look?
So the biologists say that it's actually uses the visibility radius, or 7 nearest. But in either case, there's going to be birds behind you, but it's the wing flap. Apparently you can, it's not hearing, it's more you can feel the difference in the wind. I'm not a biologist, but that's my best understanding of what the biologists believe.
So in this case, actually, it's not only the position of the influencer that affects the flock, right? It's also potentially the boundaries of the field and so on. Right? So there are obstacles that also should influence where the flock is heading.
Theoretically, although for this
Okay.
specific
Okay.
experiment, we did not consider the boundaries of the field or sonar
I
or
see.
anything like that. The flocking agents are using the flocking algorithm and just the flocking algorithm.
Right.
They would walk off the field, they would do anything like that.
In particular, this is a trial where they didn't, but you did run some trials where they did run
Of
off the
course,
field.
and like I also ran trials, like right here, you'll see that they're all actually going this direction, and now the red agent goes this way. He thinks he's walking towards the goal, but he has bad observations right now. So sometimes I ran the experiments with like the robot window on one side and the observation window on the other side. So you could see what the robots believed at the current standpoint. And a lot of times the observation window would look exactly like what you would expect. And then the robot, you'd see him walking off the field because he thinks he's walking towards the goal, but he's actually turned. That's an odometry issue that we deal with in our robot soccer team too.
I see. And in this case, the fact that the influencer has a wrong belief of his current heading does not matter to the flocking behavior itself, right? Because the influencer is telling the other agents that he's heading a particular way.
Exactly.
Right.
Okay, so we're getting towards the end. In summary, the robot implementation, we showed that the one-step look-ahead algorithm can be utilized to influence a flock of bipedal robots with very small alterations to the algorithm that was presented in an early chapter of the dissertation. Specifically, we found that we had to only consider influencing agent orientations that can be reached in one time step. One big simplifying assumption that we made throughout a lot of the work was that our influencing agents could change orientation to anything in one time step. But obviously when you take that to a real robot platform, the robots can only turn X degrees every time step, so we had to take that into consideration. So in general, the thesis question that was considered by my dissertation was how can influencing agents be utilized in various types of flocks in order to influence these flocks towards a particular behavior. There's a very long future work section in the dissertation. These are a few of the areas that I think are the most fruitful and interesting going forward. I'm happy to discuss any of these. I'm going to shortly discuss 2 of them right now. One area that I think would be really interesting is how to enter a flock. I discussed earlier in this talk that we can't use our initial positioning methods, such as the graph placement approach, a lot of the clustering approaches, because these require the influencing agents to fly into the flock. And just flying directly into the flock tends to influence the flock poorly while you're trying to reach the positions. But especially in more sparse flocks, you could potentially find a path that you could take to your desired position. It may not be the fastest, but you may be able to minimize the influence on the flock as you're reaching your placement. So that would be really interesting. And of course, I do think it would be interesting and very fruitful to extend the robot implementation to robot birds. You could use a robot bird like the one that's being used at Edmonton Airport. Make it look like a friendly bird instead of a predator, which is actually relatively simple to do. You just have to change the silhouette and the wing flap design, and then as was shown in the video from India, you can actually design a bird that birds will flock with. So I think that would also be an interesting extension. So I'm going to conclude my talk. I'm going to leave my thesis question as well as the contributions that this work made on the screen, but I'd be happy to take any questions.
All right, why don't we